Okay, so this is part 11 of our Unit 1 notes. And in this section, we're going to be looking at linear functions. And now we're going to kind of be getting an introduction, I guess, to graphing. Hopefully, most of this is review. We're just going to be looking at straight lines, no parabolas or anything yet. And then pretty quickly here, we'll be shifting gears to starting to look at parabolas and graphing parabolas. So, linear functions have four different possible slopes, and the slope is just the change of x with respect to y. So, we have positive slopes here, and as you move from left to right, they are going up, they're increasing. Our slope is greater than 0. And we have negative slopes as we move from left to right, they are going down, they're getting smaller, slanting downwards. And then we have what's called zero slope, that would be a horizontal line, and undefined slope, a vertical line. So again, slope is just, if we're given 2 points or we're given a line, it's the change in y over the change in x. Sometimes you'll hear this referred to as rise over run. And so this slope formula is what you're going to want to be memorizing and knowing and being able to use. So there's 3 different forms that we can write a linear equation in. The first one being point-slope form, slope-intercept form, and general form. Sometimes instead of general form, you see standard form. And that would be ax plus by equals c, with the constants on the other side. Those are pretty similar. Both of them, a, b, and c, all must be integers, meaning no fractions or decimals. Slope-intercept, the m and the b can be fractions or whole numbers. Same here with point-slope form. And point-slope form is a really useful form moving forward, especially those of you moving on to calculus. That will be a really helpful form for you to use. This is what we use if we have a point and we have our slope. Slope-intercept form is probably the one you're used to seeing the most. That might feel the most comfortable for you. Sometimes students will call it y equals mx plus b form, but the technical name is slope-intercept form. Now, when we have a horizontal line, the form of that equation is just going to be y equals a number. There's no x, and the slope is 0. A vertical line will be x equals a number, no y, and the slope is undefined. So sometimes these are kind of the opposite of what students anticipate. They think horizontal lines would be x equals, since the x-axis is what's horizontal. But actually, if there's no x, it's a horizontal line. And if there's no y, then it's a vertical line. So this first example here asks us to find the slope given these 2 points. So I find it's helpful if you label the points x1, y1, x2, and y2. The x values are always first, the y values are always second. It doesn't matter whether we label this the 1 point or this the 2 point, as long as we're consistent. This is both the 1 for the x and the y, and this is the 2 for the x and the y. The formula, again, is y2 minus y1 over x2 minus x1. And now we can just plug in those values. So y2 is negative 2, y1 is negative 4, x2 is 4, and x1 is 6. So on top, a negative times a negative will become a positive. Negative 2 plus 4 is going to give us 2. Let me zoom in there a bit for you. And on bottom, 4 minus 6 is negative 2, so my slope is negative 1. Now this next example is asking us to write the equation of the line given our slope and given this point here. And it's asking us to write it in these 3 different forms. So it's easiest to start with point-slope form, so that's what we're going to start with, and then we'll get to slope-intercept form and general form. I'm going to leave this space over here to write my answers, and I'm going to do most of my work over here off to the side. So I'm going to zoom out just a tad here, and we have our x1 and our y1, and then this is our slope. Remember, point-slope form above here is y minus y1 equals m times x minus x1. So y minus y1, and then our slope times x minus x1. So the only simplifying I need to do here to get it into the correct form is to make this a positive here. A negative times a negative is a positive. So y plus 4 equals negative 3/5 times x minus 10. And that's point slope form. So I'm going to go ahead and write it over here. Point slope or slope intercept form, all we need to do is get y by itself and distribute my slope here. So I'm going to go ahead and distribute my slope. So that'll become negative 3/5 x. And the negative 3/5 times the 10, a negative times a negative will be a positive. The 5 on bottom and the 10 can reduce to a 2. Negative 3 times 2 is, or 3 times 2 is 6. And on the left-hand side, we still have y plus 4. And all I need to do is subtract the 4. So that is slope-intercept form. We can go ahead and write that over here. Y equals negative 3/5 x plus 2. And then general form, we want to get everything onto the same side, and we want to get rid of our fractions. I'm going to get rid of my fractions first. My denominator here is 5, and that's my only denominator. So I'm going to multiply both sides by 5. This becomes 5y, and the 5 times the negative 3/5 becomes negative 3x, and 5 times 2 is 10. From there, I can go ahead and add the 3x over and subtract the 10 over, and I'll have 3x plus 5y equals, oops, not equals, we're subtracting the 10 as well, minus 10 equals 0. So that would be general form. Okay. So that is that example. The next one gives us an equation in general form and asks us to use the intercepts to graph. Well, if we're using the intercepts, finding our x and y intercepts, if I want to find the x-intercept, I'm going to plug in 0 for y. And if I want to find the y-intercept, I'm going to plug in 0 for x. Well, if I plug in 0 for y, plugging in 0 here, that whole term goes away, and I have 3x plus 15 equals 0. Well, if I subtract 15, let's go ahead and just write that. 3x plus 15 equals 0. If I subtract 15, dividing by 3, x equals negative 5. So 1, 2, 3, 4, 5, negative 5, 0. That gives me my x-intercept. I can solve for the y-intercept by plugging in 0 for x. 0 for x here leaves me with 5y plus 15 equals 0. Subtracting 15 over, dividing by 5, y equals negative 3. So my y-intercept is 0, negative 3. So I can go ahead and plot that point. And as long as I have 2 points, I'm able to draw a linear equation. So that's what my graph would look like. The next example says to use the y-intercept and the slope. Now, this is given to us in slope-intercept form. So we know our slope, we know our y-intercept. That's what this is here in this form. So this tells me my y-intercept is 0, 4. And this tells me my slope. So I'm going to start with my y-intercept, 0, and 1, 2, 3, 4. And my slope is negative 2/3 x. So the fact that it's negative, I know my slope is going to go like this. If you go back up to the very top of this page, we know negative slopes slope down. So I know it's going to slope down like this. It won't be like this. So it's going to be sloping down like this. And the change in y is 2. So I can either go up 2 or I can go down 2. And the change in x is 3. And I want to go in whichever direction is going to give me that negative slope. If I went down 2 and I went this way, that would give me a positive slope. But if I go down 2 this way, it gives me a negative slope. Sometimes students get confused with rise over run and confuse which way they're supposed to go. If you know you have a negative slope, you know it should be going this way. So you can either go up 2 and over 3, or you can go down 2 and over 3 as long as you have that negative slope. So I could go up 2, up 1, 2, and over 1, 2, 3. Or I could go down 2 and over 3 this way. Both of those points lie on the same line. They produce the same line here. Okay. Moving on to the next page here, we want to talk about parallel and perpendicular lines. So parallel lines have the same slope. Perpendicular lines have the opposite reciprocal slope. So if you have a slope of a over b, the perpendicular slope would be negative b over a. Or for example, if I have a slope of 3/5, the perpendicular slope would be negative 5/3. Okay. Now, as we move into higher levels of math and we start looking at not just linear equations, but any kind of equation, we can talk about what's called the average rate of change. And the average rate of change is just the same thing as slope. It's the same formula, but we can use it in referring to other types of equations. So notice that this is no longer a linear equation here, but we can talk about the average rate of change from one point to another point. And so the formula is the same thing, the change in y over the change in x. That's what these symbols mean here. And we're just taking the y value of the second point minus the y value of the first point, and then x2 minus x1. That's the same as slope formula. So this really just means the same thing as y2 minus y1. It's just using function notation. So we're going to use that formula here in these next examples. It says write the equation of the line in slope-intercept form that passes through this point here and is perpendicular to this line. Well, before I can go any further, I need to know what the slope is of this line to find out what slope is perpendicular to that. So I'm going to go ahead and get y by itself. I can add 12 to both sides and subtract x. And I'm left with 7y equals negative x plus 12. And then I can divide by 7 everywhere. And then that becomes y equals negative 1 over 7x plus 12 over 7. Now, don't get too worried about this 12 over 7. I don't really actually need that. All I need is the slope. And the perpendicular slope to this would be the opposite reciprocal. So it would become 7 over 1 and the opposite sign. Well, this is negative, so the opposite sign would be positive. So I know the equation that we're looking for has a slope of 7. Well, if I know my slope and I know this point right here, I can use point slope form to get me started here. So y minus y1 equals slope 7 times x minus x1. Can simplify that to y plus 9 equals 7x, and I'm going to distribute that negative 35. And then to get y by itself, I would just subtract 9. And y is equal to 7x minus 44. And that's the equation that is perpendicular to this line and goes through this point. The next example says find the average rate of change of the function from x1 to x2, where f of x equals x squared minus 2x, and we're looking at x1 is 3 and x2 is 6. So if I want to find f of x1. Well, that's f of 3, and that's just plugging that into the function. So 3 squared minus 2 times 3, well, that's 9 minus 6, which is 3. If I want to find f of x2, that's just f of 6. I'm plugging in 6 to the equation now. And that gives me 36 minus 12, which is 24. So if I'm using this formula here, my average rate of change, f of x2 minus f of x1 over x2 minus x1, that'll be 24 minus 3 over 6 minus 3. Well, that's 21 over 3, which is 7. So my average rate of change is 7. Now we can also talk about the average velocity of an object. This is again the same formula, it's just different variables. So in calculus, you'll see s of t a lot. This is called the position function. And it's just the change in s over the change of t, the same as change in y over the change in x. Okay. So these t values behave like x's, s of t is like f of x. So s of t is the function 5t squared. It represents a ball rolling down a ramp. T is time in seconds after the ball is let go. S of t is the amount of feet traveled. We want to find the ball's average velocity from t1 equals 2 to t2 equals 3. So we want to find s of t1 and s of t2. Well, s of t1 would be s of 2 and s of 3. And the function is 5t squared. So 5 times 2 squared and 5 times 3 squared. 2 squared is 4. We do exponents first. Remember our order of operations. So 4 times 5 is 20. 3 squared is 9. 9 times 5 is 45. So that would be 45 minus 20 over 3 minus 2, which is 1, and 25. So 25, and because we're talking about a specific word problem with actual units here, we want to say feet per second. All right. Now this next page, let me see if I can zoom out a bit here, is a list of all of our parent graphs. These are the most basic functions we can look at. So here we have our basic linear function, y equals x. And it gives us a bunch of information here. It's linear, it's an odd function, the domain and range, and end behavior, which we'll talk about more in Unit 2. We have the absolute value function, x squared, square root of x to the third power, cube root of x, b to the power of x, which is an exponential function, a log function, rational functions, all kinds of functions. In fact, probably more than you really even need. And then we have our constant function down here. So these are really just a reference for you because you'll see different kinds of functions in this section where maybe we have the cube root of x and you want to know what that graph looks like. And the way we're going to use this is by looking at transformations of all of these graphs. So we are going to be shifting them up, down, left, and right, stretching and shrinking and manipulating them in different ways. So if I add a value on the end, that's a vertical shift up that amount. If I subtract a value on the end, it would be down that amount. On the inside, adding is to the left. On the inside, subtracting would be to the right. A negative out front would be reflecting over the x-axis, a negative inside over the y-axis. Multiplying by a value out front would stretch it or shrink it, and then multiplying inside would be a compression or a stretch, depending on if that b value is greater than 1 or less than 1. That being said, this is easiest to understand by seeing some examples, so let's get into a few examples here. So the first one, we have the square root of x and then minus 3 on the end. Notice that minus 3 is not inside the square root. So the fact that this is on the end here, not inside the square root, means that this is a vertical shift. Again, if it's on the end, it's a vertical shift. So this would be moving it up, this would be moving it down, this would move it to the left, this would move it to the right. So minus a value on the end would move it down 3. So the first thing we're going to graph is just our most basic square root function, the parent graph, and then we're going to graph this function after that. So the parent graph of the square root function we can see on that chart right here. This is what it looks like. But you could also just think about plugging in some values. So I'm going to graph that first one. Let's say y equals the square root of x. And if I plug in 0, I get 0. If I plug in 1, the square root of 1 is 1. And I'm going to plug in values that I know the square root of. So I'm not going to plug in 2, I'm not going to plug in 3. The next value I'm going to plug in is 4, and the square root of 4 is 2. So we have an idea of what that graph looks like. And when you're graphing more than one graph on a single piece of graph paper here, you want to label them. So I labeled this one y. And then g of x is that shifted down 3. So I don't need to come up with new points. I'm just moving all of those points down 3. So down 1, 2, 3, and down 1, 2, 3. And there's my graph. And that's g of x. So we can do this with any type of function. This next one here shows us the absolute value function, and so the parent graph there would just be y equals the absolute value of x. And looking back at that sheet we have here, the absolute value function is just like this. It's a sharp V, just like this here. Okay. So, again, I could plug in some points if I wanted to. If I plug in 0, the absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. 3 is 3, so on. Absolute value of negative 1 is 1. The absolute value of negative 2 is 2, 3, and so on. And that's y. And then this shift here, on the inside, we have a plus value. So remember, on the inside, that would move it to the left if it's a plus. So plus 1 means we're moving left 1, and minus 2 on the end means we're moving down 2. So each of these points, starting here with this vertex point here, we're going to move left 1 and down 2. Left 1 and down 2. Left 1 and down 2. And over here, left 1 and down 2. Left 1 and down 2. And now I can go ahead and draw that shifted graph. And that is h of x. Let's practice a couple more, and then that'll be the end of this video in this section here. So we have negative 2 x plus 2 squared plus 1. And that parent graph would be the x squared function. But I'm actually going to have us use y equals negative 2x squared. And the reason why is because this negative 2 up front does two things. The 2 stretches our graph vertically, and the negative reflects it across the x-axis. So normally the x squared graph, and if we look back at that chart real quick here, the x squared graph goes up like this, but if I multiply by a negative out front, it will go down like this. So if I wanted, I could make a table of points. I could plug in some values, let's say negative 1, 0, 1. If I plug in negative 1 squared is 1. 1 times negative 2 is negative 2. 0 squared is 0 times negative 2 is still 0. 1 squared is 1 times negative 2 is negative 2. So I can go ahead and plot those points. And we see our parabola curving down this way, and this is y. F of x, this plus 2 is going to shift us left 2, and this plus 1 will go up 1. So all these points will go left 2 and up 1. Left 2 and up 1. Left 2 and up 1. And this is the shifted graph, f of x. Okay. Now this next one, I'm actually not going to use the parent graph because there's no horizontal or vertical shifts here. I'm just going to go straight to the answer graph. And what we could do is we could plug in some points, but I also want to reference that chart. This is x cubed, and the x cubed graph generally looks like this. We have a negative out front, so it actually gets flipped, and a 1/4 out front, so it's getting flattened. If you kind of think about it going like this and then shrinking it, flattening it a little bit. So I'm going to plug in some x values, and because I have this 1/4 out front, I want to pick x values that are divisible by 4 so I don't have fractions. So I'm going to choose 0 as one of them. but I'm also going to choose -2 and 2. -2 cubed is -8. -8 times -1/4, well, a negative times a negative will be a positive, and 8 times 1/4 will be 2. So we can go ahead and plot that point. 0 cubed is 0 times -1/4 is still 0. And then 2 cubed is 8 times -1/4 is -2. Now this is not a straight line. We already saw on our chart the shape of a cubic function. So it's still the shape of that graph, just through those points. We won't get too far into these kinds of translations, but this is a good introduction to it, and we'll go ahead and end this video here.